Hello and welcome to the fifth lecture on ordinary differential equations. In this lecture, I'm going to briefly discuss the differences between linear and nonlinear equations. Perhaps one of the important ones is the existence and uniqueness of solutions. Um, for linear equations, we have a neat theorem here. I call it theorem 2.4.1 just to be the same as the theorem, to have the same number as the one in the textbook. It describes the condition and the situation for a linear equation, for a linear differential equation to have a unique solution. Okay, so let's just go through the theorem together. You should recall that this is the general form of a linear differential equation, and pt and gt are just functions of t, no y included, and the other parts of the equations are y prime and y. So the theorem says that if the functions p and g are continuous, not everywhere, but on an open interval alpha beta, okay, where this open interval includes the point t0, then there exists a unique solution or function y equal to phi t. You should notice that we're following the same notation as here, where we used phi. So there will be a unique phi that satisfies the differential equation. Well, yes, for sure, a solution should satisfy a differential equation. For every, this is perhaps the important part, for every t between alpha and beta. And note that this is the same as the previous interval. This is the first part, and the second is that it also satisfies an arbitrary given initial condition. So yt of 0 being equal to whatever y0 you want. So the main part of this theorem, the emphasis is that as long as p and g are both continuous on an open interval, then you are guaranteed to have a unique solution in that open interval, given any initial condition. Okay? So let's go through an example. It says use the above theorem to find an interval in which the initial value problem, this, has a unique solution. Okay, so let me first write this equation in the form of the above theorem. It will be y prime plus 2 over t times y, and of course I'm assuming that t is not equal to 0, is equal to 4 times t. So now this is my p and this is my g, right? Okay, so this function is continuous on R. It's simply continuous everywhere. However, this one is continuous on not at t equal to 0, so it's basically continuous on the open interval minus infinity to 0 and 0 to plus infinity. Now, the initial condition here, this is for t greater than 0, right? So that means this is really what we should look for. tells me that for t equal to 1, y should be equal to 2, and therefore t should belong to this interval. So therefore, this is really the interval I should be looking for. So in the initial condition, the interval is 0 to plus infinity. Okay, so we are guaranteed that in this interval there is a unique solution for this differential equation. And actually, if you go, we did solve this equation in our previous examples. The solution is y equal to t square over plus 1 over t square, and this holds for all t greater than 0. So it matches what we have found before. Okay, good. The situation is more difficult, and we have a way weaker result for nonlinear differential equations. I have rewritten the form of the theorem here so that the matching to the previous theorem becomes more evident, I mean, compared to the book. So let's go through, let me just emphasize that this one is for linear, okay, and this one is for non-linear differential equations. Okay, so if the functions f and partial derivative of f with respect to y, so these are kind of a dual of p and g over there, are continuous. Now, because we have both t and y, right? So it won't be just a simple interval, it will be a rectangle, okay? So previously we just had t between alpha and beta, now we have a rectangle because it will be both t and y in the ty axis. So if they are continuous on some rectangle containing the point this time, because again we have a t, we have a y, so it should include this point t0 and y0, then there exists a unique function or solution similar to the one above, the above theorem, y equal to phi t, that obviously again it should satisfy the general form of a first order differential equation. But then here, this is the very important part. The interval that it supports, it's not the same as the rectangle. So you see the interval now is t not between, it's not like alpha beta, it's an interval around the point t0. Okay, this is for some value of h. So it is for sure contained in alpha beta, but it's not necessarily the same. In the previous theorem, you see that, here we had alpha beta, and then the theorem stated that the solution exists in the same interval, alpha and beta. Here, this alpha and beta is it's not necessarily the same as this one. It only contains this smaller one. So this is just, it's like t0 plus minus h, okay, the interval that we're looking for here. So anyways, let me just avoid these distractions. So again, first, there is a unique solution, not in alpha beta, in some subset of this, or subinterval of alpha beta. And then second, it satisfies the initial condition. So the second part is the same as before. It's just any initial condition that we will have. So you see the main difference is that, well, first of all, instead of p and g, we have now f and partial derivative of f with respect to y, and then which of course results in a rectangle rather than an interval. But then more importantly, this theorem is way weaker than the previous one. It only guarantees the existence of such unique function for just some interval t0 minus h and t0 plus h, which we have no clue how it looks like. Okay, so it's more of a guarantee type of theorem rather than the previous one that also states for what interval that solution exists. Okay, so let's go through an example to explain this. Example 10 says, consider the initial condition problem here, y prime equal to this term, and we have 4 parts to answer. First part A says, is theorem 2.4.1, which is for linear equations, is it applicable to this equation? Now, if this is going to be applicable, well, you need to have a linear differential equation. Clearly, this is not linear, right? Because look at this. This is y dot, and then you have equal to a term. Well, this is perhaps my together with the 2. Maybe you can call it p of x. But then here, this is not linear. It's just 1 over 1 y minus 1. If I had, instead of this was just y minus 1 in the numerator, then that might have been, that could be a linear differential equation, but not in this form. So no, because it's not linear. No, because the equation is nonlinear. Well, it's not linear, I would say, yeah. Yeah. Okay. So that's with part A. Now part B says apply theorem 2.4.2, which we have here, to this initial condition problem, and well, it definitely expects us to state the outcome, the result that the theorem is stating. Okay, so in order to apply that theorem, what we need to do is to first determine the continuity of f and the partial derivative of f with respect to y. So to just facilitate this process, I have already written both f and the derivative with respect to y. That derivative with respect to y is not complicated. It's just 1 over y type of derivative, which it will be minus 1 over y squared. Okay, so we have these two terms. Now, the point is that both of these are continuous everywhere except on the line y equal to 1, right? So both are continuous everywhere except for y equal to 1. Okay, so the interval or the rectangle I'm looking for should not include 1. Now, so the initial condition, well, I mean, for example, when you have something like this, then the acceptable intervals for the continuity, of course, is, or it should be R. are, so y, it should be either in minus infinity to 1 or 1 to plus infinity. Good. Now, because of this initial condition, which says for x equal to 0, I should get y equal to minus 1, then obviously this is the interval I'm looking for. And that brings me to this interval, right? Okay. So, x of course can be can take any value, or x is corresponding to t in that theorem. I don't have any issues there. Now, for this interval, the theorem states that because I have found an interval where the initial condition lies, the theorem states that there exists some interval for x that around the point x0, my initial condition. This is, if you want to know where I'm giving this initial condition, it's exactly here, t0. So it should be tx in x0 minus h and x0 plus h, which is basically the x0 here. Just to be clear, this means x0 equals to 0 and y0 equals to minus 1. Okay, so it's then in the interval minus h and plus h, there exists some such interval where there exists a unique solution. Or let me just write it down in this way. A unique solution to the equation exists. Okay, so let me draw this. Oops, it's good to have this tool. Okay, so if I have, well, x and y, so I know that for y equal to 1, this is 1, I know that either on the upper part, or the part below, we have a continuous solution. But then, and the initial condition, by the way, is 0 and minus 1. So I really need to continue this line. This is the initial condition. So again, the continuity was telling me that both f and the partial derivative of f are continuous here in this part, or the part above, but this is where I was interested in, because, and this is the rectangle. Okay, it's y less than 1, and x is just simply between plus and minus infinity. So it's telling me that in this rectangle, both of those functions are continuous, and therefore there will be, let me just read from the theorem, there exists a unique solution phi that satisfies this differential equation for some interval x between x0 minus h and x0 plus h. So it simply is telling me that in such a small interval, well, we don't know if it's small or not, but I know that this is h, the length of this thing. So for x between minus h and h, in this area there will be a solution which is unique. Okay, so if I draw really the border of this, let me just draw this. So that's x between minus h and h is giving me a rectangle. It saying for this interval, which again I don't know the value of h, but somewhere here there will be a unique solution that passes this point 0. So for example, it might be something like this. Okay, the point is that in this little, again, this little yellow part, I will not have multiple solutions. Like I cannot have another solution passing through it. That's all that this theorem is telling me, right? So nothing more. So if, for example, it's not telling me what will happen in this area or in this area out of the yellow part. Okay, so now that is, we already did part A, we did part B. Now it says repeat part B when the initial condition changes to y0 equal to 1. Okay, well, for equal to 1, f and the derivative with its derivative with respect to y are not defined. So we cannot apply the theorem. It says they should be continuous in some rectangle, right? So they should be continuous, but they are not continuous in this case for any rectangle that covers this, that covers this initial condition here. Right? Because then, sorry, not for it. It's now the initial condition will be this point. And we know that on this line of y equal to 1, the solution is not continuous. Well, the functions f and its derivative with respect to y are not continuous, so I cannot find any rectangle like this so that I guarantee that this, both of those functions are continuous here. So part C, the answer is that the theorem cannot be applied. Okay, because such a rectangle cannot be found. Okay, now let's go to part D. It asks, does the equation have a solution when we change the initial condition to y0 equal to 1? Okay, now just note that what happened in part C was that we just found that the theorem cannot be applied in this case. Now, the theorem not being applied does not mean that there does not exist a solution or even a unique solution. It simply means that this theorem cannot be applied. So part D is asking, well, okay, that theorem cannot be applied, but is there a solution? Can you find any? Now, if you look at this equation, you should be able to solve this using what you've learned from the previous lectures. It's separable, right? So I can just multiply 2 times y minus 1 times dy. This should be equal to the other side. Right? So I just multiplied the numerator in dx and the denominator in dy. And well, this is not difficult to solve. You can simply see that this was really just y squared and this was 2y. This was x cubed plus 2x to the power of 2 plus 2x plus some constant c. And again, you can solve this and see that y will be 1 plus minus the square root of x3 to x2 plus 2x. And oops, I forgot to determine the value of c. Well, we need to have the initial condition 0 and 1. If I put 0 for x, then this will be 0, and this will be for 1, this will be 1 minus 2, and which is minus 1. Therefore, c will be simply minus 1. Now, if you solve this, you will get this solution y equal to 1 plus minus this square root. Now, is this a solution? Yes, it satisfies the initial condition, and we have a solution. Actually, if I put x equal to 0 here, I will get 0, and then I will get 1 for y, regardless of the plus or minus. Okay, so actually we found two solutions. Both the plus and minus work here. Okay, so the answer for part D was yes. Okay, so again, even though the theorem did not give any result, we could not apply it, there did exist a solution. Actually, in this case, two solutions. Okay, so this emphasizes the difference between these two the whole example. The previous theorem, it was quite sharp. It helps to determine the interval where the whole interval where the solution exists and is unique, whereas the second one just says, well, there is some interval where the solution exists and is unique, and it doesn't say how big that interval is. It just says it exists. Okay, so that was one of the main differences between linear and nonlinear differential equations. The second difference is the interval of definition. So going back to the theorem we just presented for linear equations, we had that, because again, we had these two intervals, t between alpha and beta, where both p and g are continuous, is the same as the alpha beta, the interval where the unique solution exists. And that is quite helpful, because then according to the theorem, the solution of a linear equation in the general form, so this was just the form that we had there with some initial condition, exists throughout any interval about t equal to 0 to t0, right? So there, this interval is basically the alpha beta that we had there, in which the functions p and g are continuous. So as long as p and g are continuous, that interval exists. That the uniqueness and the existence of the solution is guaranteed. So you just need to find that interval where P and G exist again, and it's continuous, and that interval is sufficient for being the interval of definition of the solution. So for example, if you had 1 over t as pt, then you would say, well, it is not defined for t equal to 0, so I will consider 0 up to plus infinity or minus infinity to 0 as one of the intervals for the definition of the solutions. Now also, 1 over t is continuous on both of them, so we're good. Now imagine gt was just t, which was continuous everywhere. Then based on the initial condition, one of these, for example, this would have been chosen, and this same interval was the interval of definition. You don't need to do any extra calculation. That is quite handy. But, well, this does not hold for nonlinear equations. Okay, no longer holds. To see this, let's proceed to this example. We have y dot equal to y square with the initial condition y0 equal to 1. So the first part says apply theorem 2.4.2. So if we apply this, we see that this is my f function, right? This is the function of t and y. So for part A, I will have f. If you recall, we should have written f and the derivative of f with respect to y. Okay, so f of t, there's really no t here. I can just simply write it down as y. F of y equals to y square, and the partial derivative with which in this case will just turn into the derivative with respect to y, which will be equal to 2 times y. Both are continuous on R, on the whole interval R. So therefore, the theorem guarantees that a unique solution exists on some interval around, this is x0, this is y0 again, around minus h to h. Okay, so there will be some unique solution. Now part B, so at least we know there will be a solution. That's good, and that solution will be unique on this interval for whatever value of h, which we don't know. Part B says now, okay, solve this equation. Solving this equation won't be difficult. It's just y dot. I would like to write it down in this form, y minus 2 to the power of minus 2 equals 1, right? And therefore, this was really y minus 1 to the power of minus 1 with a negative sign, and the right-hand side was t plus some constant c. And if you solve this, you will get that y is equal to minus 1 divided by t plus c. And to satisfy the initial condition, y will be minus 1. I want it to be equal to 1 at t equal to 0, so c should be minus 1. Oops. Okay, good. Now I'm done with part B. Part C. Determine the interval in which the solution exists. Okay, well, I'm just going to use the definition of a solution in this case, because the theorem is not telling me much. It's just saying for some interval around minus h to h, there will be a unique solution. Well, in this case, we have a solution y equal to minus 1 divided by t minus 1. We have this solution. And we know if we take the derivative, then we will go all these steps back, right, until we reach here. And it means that this, oops, sorry for that. It means that this differential equation will be satisfied for our solution over here. But as long as it is differentiable, so we need it to be continuous, and we need the differentiation to also exist. So the differentiation obviously, and well, actually y itself will exist not for t equal to 1, right here. Cannot have it to be defined for t equal to 1. But for anywhere from t greater than 1 or anywhere t less than 1, it looks like the differentiation exists. Okay, but again, since the initial condition is 0, it's t equal to 0. Sorry, this is the same as t0 here. I was confusing x0 and t0. So let me just write it down. For t greater than 1 and t minus 1, less than 1. But then because of the initial condition, which is t equal to 0, this is the interval of interest. Again, this is because of the initial condition. So the interval in which the solution exists is minus infinity to 1. Okay. And again, the reason is because if I use this function y equal to minus 1 divided by t minus 1, in this interval, this function is defined, and I can take the differentiation. For any point here, I can go back all of these steps until I reach the equation up there, the differential equation. So it is a solution. Now, the purpose of this example was somehow to show that first of all, we cannot immediately use something like theorem 2.4.1, where as long as we find where PT and GT are continuous, then we can say that the interval of definition is the same as that interval. Such a thing does not exist for nonlinear equations. And secondly, well, actually the whole theorem 2.4.2, it may not tell us much, and we may need to solve the whole equation. Well, if we can. Okay, good. So now let's proceed to the third difference between linear and nonlinear equations. For linear equations, we have a notion called general solution. So again, for a first-order linear differential equation, it is possible to obtain a solution containing an arbitrary constant such that all possible solutions follow by specifying values for this solution. For example, if you consider this differential equation, the solution, the general solution, you can easily find that it's c, a constant c times e to the power of t. And you have seen this constant c appearing in almost all of the previous examples. And for a linear equation, all of those solutions will be just in the same form, c e to the power of t, just the value of c would differ. So sometimes it's 0, sometimes it's 1, or whatever value. Now, this notion of having such a general solution, this does not necessarily hold for nonlinear equations. So, for example, in this in the above example, we had the solution was y equal to -1 over t minus 1. And okay, let me just show it here. This was really the general solution. We had this constant c, and we could give it different values. In the above example, we gave it -1. Yes, so this indeed is giving a class of infinite number of solutions. Okay? However, it does not cover all solutions. It's not general. Because, for example, y equal to 0 is also a solution of this differential equation. Here. If I put y equal to 0, the left-hand side, well, the derivative of 0 is 0, and the right-hand side, we have 0, so it matches. Not for this initial condition, but it is a solution to that differential equation. However, this y equal to 0 is not captured by this equation. This does not hold. Okay, so again, this whole part was to just show that such a notion of general solutions does not necessarily exist for nonlinear differential equations. Okay, good. Another difference is about the implicit or explicit solutions. Well, actually, the whole notion of solutions itself. For an initial value problem of a first order linear differential equation, we did show in the previous lectures that this is the general solution. Again, you don't need to memorize this, but this is the general form of the solution where mu t was the integral of another function. This, well, we have the solution here. We have y equal to something, right? It's in this sense, it is explicit. It's completely explicit. However, for nonlinear differential equations, even for the first order, typically the best we can hope for is such an equation, and a mixture of t and y, like for example, t squared plus yt plus like ln of y is equal to 0. Okay? And this is not an explicit solution. It's not like y equal to something. It is an implicit solution. We call such a solution, or this equation, perhaps I should say, an integral or first integral. Okay? Now note that even this is only possible for limited type of equations. So we may not even be able to find such a solution. So if it is separable, then of course we can get this, but not for any general nonlinear differential equation. And that's another main difference. Perhaps this is the greatest difference between the two. That for many nonlinear, for a huge class of nonlinear differential equations, perhaps for the majority of them, we just cannot get even an implicit equation. Okay? And in that case, this brings us to the last difference I want to cover here. We should just go with numerical or graphical representation of the solutions. Okay, so we already covered how to draw like the direction field where we had x on one side and y on the other axis, and we could draw like these arrows showing the derivative of y with respect to x and so on, right? You should remember this from our very beginning examples. This is quite helpful. For linear differential equations, the purpose of drawing this is mainly for illustrative purposes. But for nonlinear equations, most of the time, this is the only possible tool that can help us. It's the only possible way to understand the solution. And typically we should do this with the use of a computer. And of course, there are also ways to solve this equation numerically. The idea is similar to what we draw for a direction field, but we will discuss this later in this course. So again, when it goes to nonlinear equations, unless it's of a particular type that we know the solution, then we mainly need to rely on graphical representation of the integral curves or the numerical like solutions. Okay, like we try to obtain this equation or solve it numerically. So these are the main differences of the linear and nonlinear equations that I wanted to cover. Thanks for your attention.